After the mesh is completed, the pre-processing stage is over, and it's time to move to the CFD solution. The first step is setting up the solver. This involves defining material properties for your fluid, and possibly solid and/or mixture properties depending on the problem. The next step is activating the physical models required by the problem, and this might mean selecting which turbulence model to use, or which combustion model, or multi-phase model, and again the required selections depend on the specific problem that's being solved. Then you need to set operating conditions, define boundary conditions, and provide initial values for the solution, which could in some cases be the solution of a previous simulation. To complete the setup, you need to define the solution control settings, although for many cases there's no need to change the default values, and to define your convergence monitors. This is obviously just a quick outline, and as the course proceeds, we will cover each of these items in more detail so that you know exactly what needs to be done. In the left-hand side of this slide, there's a very useful suggestion for setting up complex problems, especially when it's your first time using certain kinds of physical models. In many cases, it's not necessary to change the default solver settings, but for certain more complicated physics, and in the example here this is a transient multi-phase free surface flow, some amount of trial and error might be necessary to get the solution up and running. In cases like this, building an auxiliary two-dimensional approximation of the model can allow you to figure out quickly what settings are needed, much more quickly in general than with the full three-dimensional model, so that means that when you go to the actual 3D model, things will go smoothly from the start. In many years of working as a support engineer, I've seen over and over how effective this strategy can be. After the solver setup is finished, you're ready to compute the solution, which means telling Fluent to solve the discretized conservation equations that we discussed earlier. The most efficient way of solving these equations is to use iterative methods, which is what Fluent does, in which a number of successive iterations are performed until the solution converges. When we talk about a converged solution, this means a number of things. Firstly, when the solution is converged, the solution variables no longer change from one iteration to the next, no matter how many additional iterations are performed. One way of checking this is to look at the residuals. Residuals will be discussed in more detail in a later presentation, but they basically represent the difference between the right-hand side and the left-hand side of the equation on slide 4. The graph on the left is a plot of the residuals from a CFD simulation, and what we look for is that the residuals for all of the equations begin at a relatively high level at the start of the calculation, and then as Fluent performs iterations, the residuals gradually decrease until they all fall below some threshold that tells us the equations have been successfully solved. Besides residuals, we also want to do mass and energy balances on the boundaries of the domain in order to ensure that property conservation has been achieved, and probably most importantly, we want to ensure that our quantities of interest, and depending on the problem it might be drag or pressure drop or temperature, whatever it happens to be, that these quantities have reached steady values and no longer change as the solution iterates. To do this, it's typical to set up plots similar to the residual plot, in which we plot monitors of the quantities of interest versus iterations. It's critical to ensure that the solution is converged, but once it is, it's also important to realize that the accuracy of the converged solution depends on many factors, including the appropriateness and accuracy of the physical models, assumptions made, mesh resolution and independence, and numerical errors. Finally, as it says on the left, when we have a converged and mesh-independent solution on a well-posed problem, it will provide useful engineering results.